Hi, my name is Céline Coutrix, and I will present a paper I wrote together with Camélia Prost on mobile tactile interaction. Today, the most widespread form of computers is the mobile phone. The SIGCHI community has been very actively working for mobile users. We have even had a dedicated conference, Mobile SIGCHI, since 2005. As an SIGCHI professional, maybe this happened to you too. Sometimes we participate in our colleagues' experiments. This happened to me a few years ago. I took part in an experiment studying mobile interaction on a touchscreen. This completely changed my perspective because I experienced a problem I never thought of before. For you to also see this problem that a large part of mobile users experience, I want to provide you with new glasses. What do you see now? This may be better. Yes, she has long nails. And so do many users around us, men and women. And so did I when I took part in this experiment, and I struggled to perform the task I was asked to perform. Although, as HCI professionals, we informally see users with long nails struggling with their mobile phones. They are very seldom reported or included in our research. With this paper, we want to convince you that it is important to design for people with long nails too. Beyond personal experience, we wanted to take a scientific approach to explore how much users with long nails struggle to use current mobile phones. Our first research question was to identify the effects of long nails on mobile tactile interaction. We conducted a formative qualitative study interviewing 14 participants with long nails. We managed to include 5 men in our participants. When these participants talk about their reasons why they have long nails, they mention habit, aesthetics, practicality, artistic practices like playing the guitar, and professional obligations like being a beautician. Overall, asking users to cut their nail to fit our standard user is not acceptable. Having long nails is a social practice that some users can hardly avoid. Most of them already thought about the impact of long nails on touch devices, either by noticing on themselves or on someone else, or when someone else commented their own use of the touch device. Our participants also mentioned hand grip issues when they have long nails. On the left-hand side, you see a participant who has a ring at the back of the mobile phone for a better grip. On the right-hand side, you can see another participant who needs to stretch her finger so much to touch her target that she almost loses her grip on the mobile phone. Our participants also complained about not being able to touch the screen with their fingertips, which seemed to them like the right way to use the mobile phone. Another problem they mentioned was the lack of accuracy when trying to tap on a target. They often miss targets, but also suffer from this indirectly. For example, when this guitar teacher uses his non-dominant hand with the mobile phone. The last thing we wanted to highlight from the qualitative study is their comments on the different types of nails. Participants mentioned that the longer the nails are, the more difficulties they have with their mobile phones. They also interestingly mentioned that artificial nails are different from natural ones, because particularly the grip is not as strong as that of natural ones. After this formative qualitative study, we decided to measure the magnitude of the most mentioned effects in the interviews. The first one we investigated is the pitch angle. We measured how vertical participants could place their finger on a touch surface. They started with the finger flat on the surface and raised it until their nails touched the surface too. And then they put their finger flat again on the surface. We recruited 12 participants to do so 3 times for the thumb and index fingers, and with short nails and 5 and 10 millimeter long artificial nails. Here are the results of this experiment. You can see the range of pitch angle in degrees on the x-axis. The ranges lie between the minimum pitch angle and the maximum pitch angle. The values for the thumb are in light gray and for the index finger in dark gray. At the top are the ranges for 10 mm nails, in the middle the ranges for 5 mm nails, and at the bottom the ranges for short nails. We found that users lose an average of 27% of their range of pitch angle when they have 5 mm long thumbnails compared to short thumbnails. Users lose an average of 53% of their pitch angle range when they have 10 mm long thumbnails compared to short ones. You can find detailed results in the paper. Given that prior work found that the pitch angle is related to accuracy, you can imagine how much users with long nails struggle with their current mobile phones. This graph shows the touch ellipses for each finger and each nail length collected for one participant. The red lines show the direction of the major axis of the touch ellipse, and the arrows show the minimum of the major axis. We notice that the longer the nail, the larger this minimum. This allowed us to build individual models for each participant. The geometric model is not sufficient because of the large variation in the finger anatomy. These models can estimate the user's nail length on the y-axis based on the measurement of the major axis of the touch ellipse on the x-axis. This shows that we already have a basis to customize the interaction techniques for users with long nails. Another point that was commented a lot in our formative interviews was the unstable grip. To study this, we measured the impact of long nails on the comfortable area in particular. We also gathered data about the useful area, and you can find these results in the paper. We asked 12 participants to draw the largest possible area without moving their grip on the mobile phone. That is, they only moved the IP, MCP, and CMC joints of the thumb. Again, with the same 3 different sizes of artificial nails. Here are the areas that we collected for each nail length. Users with short nails have an advantage of almost 20% more comfortable area compared to users with 5 mm nails. And users with short nails have an advantage of 36 more comfortable area compared to users with 10 mm nails. This is a serious decrease in the area that users can reach comfortably. I showed earlier the uncomfortable grip of this participant in the formative study. Although one could think that such an uncomfortable grip is also experienced by users with short nails, this experiment shows that the magnitude of this lack of comfort is not comparable. To make sure that these results also apply to users with natural nails, and to take their expertise into account, we also collected data from additional participants who had natural long nails. In this figure, the black dots are from the 12 participants of the experiment with artificial nails, and the gray dots are from the 12 participants with natural long nails. The x-axis shows the nail length, and the y-axis shows the size of the comfortable area in square centimeters. You can see that the comfortable area might decrease even faster with naturally long nails, as the slope of the red line is steeper than the slope of the blue one. We then wanted to predict if a pixel can be reached comfortably when a user has another nail length. I showed the example of participant number 9 here. The collected comfortable areas are white on top of the mobile phone screen shown in black. Let us consider a new nail length that we did not measure, 3 mm for example. Based on the data we collected during this experiment, can we say if a pixel will be inside or outside the comfortable area? We modeled this with polynomials of degree 2 to build such per-pixel prediction models. Here is what we obtained for each participant. We are sure whether a location is comfortable when we are far from the boundaries of the comfortable areas. We can see that models make sense for single users, as other factors like the size of the hand play a role. In addition to the pitch angle and the unstable grip or comfortable area, accuracy was another point that was commented a lot in our formative studies. To study this, we measured the impact of long nails on target acquisition efficiency. We asked 12 participants to acquire targets of varying width and distance, arranged in a circle. The targets could either be inside or outside the comfortable area. Participants acquired targets with the index and the thumb, and with the same 3 different sizes of artificial nails. On the x-axis is the throughput, in bits per second, that we found for the index finger. The nail length is on the y-axis. We can see that the interface makes the users lose 13% of throughput with 5 mm nails compared to short nails, and 20% of throughput with 10 mm nails compared to short nails. Here is the throughput for the thumb. We can see that the interface makes users lose 14% of throughput with 5 mm nails compared to short nails, and 29% of throughput with 10 mm nails compared to short nails. We also gathered interesting qualitative results in this experiment. The first thing is accuracy. I show you the selection position of the missed targets on the mobile phone here, with the comfortable area collected in the previous experiment. For the thumb, the missed positions are denser at the top left edge of the comfortable area, showing that the lack of comfort decreases the accuracy of users with long fingernails. However, for both the thumb and the index finger, targets are missed in all locations, including in the comfortable area. The second most commented issue was the screen occlusion by the long nail. Participants mentioned, for instance, that you cannot see the surface because of the nail. The last point is the extra effort users with long nails must deploy to reach the same efficiency level. For instance, they felt a higher cognitive load because they tried to make up for the extra difficulties like the visual occlusion or the unstable grip, for instance. And they felt more tired afterwards, or felt pain in their fingers or wrists. Again, to make sure that these results also apply to users with natural long nails, and to take into account their expertise, we also collected data from additional participants who had long natural nails. In this figure, the x-axis shows the length of the nail, the y-axis shows the throughput. The top graph shows the data for the thumb, and the bottom graph shows the data for the index finger. The black dots are from the 12 participants of the experiment with artificial nails, and the gray dots are from the 12 participants with natural long nails. We can see that the tendency is the same. As a takeaway message from this presentation, we highlight a few recommendations. The first recommendation is for our rationale for recruiting participants in our experiments. Please include participants with long nails to assess the usability of current or future techniques for them too. Our second recommendation is for design. As a community, we should generalize techniques that improve precision, such as the shift technique illustrated here. I showed earlier that the system should be able to estimate the user's nail length based on the minimum length of the major axis of the touch ellipse. The zoomed call-out view could be shifted even further depending on how long the user's nails are. Our second design recommendation is to use more extensively techniques that improve the reachability to areas that are not comfortable. I show you here the example of a technique using the tilt angle of the phone, for instance, to shift the screen towards the comfortable area. Our last recommendation is to avoid techniques that rely on a large pitch rotation or large comfortable area. Many interaction techniques proposed so far rely on pitch rotation, for instance, such as fat thumb in 2012 or micro roll in 2009. Thank you for listening to me. I hope we will now all pay attention to users with long nails.